Yeah. It's recording?
You're on TV.
Well, you're recording.
Rewind tape.
Reporting for Fox 11 News at 4 with the latest information on the basic idea that basketball, like every sport, enforces the idea of physics. Unfortunately, it just came in. The decrease in the generation's height, the deficiency has significantly affected this season's ranking. Though height is not the importance of the sport to win, the simple ideas of projectile motion, accurate acceleration, and using the right angle to start the initial motion of the ball and all factors. Let me turn it to SDSU's basketball court to observe the team at work. Ashley Bennett is a lucky person to be able to catch the amazing footage and to show how physics is applied to the very physical sport of basketball. Thank you.
Thank you, Krista. I'm here at SDSU's basketball court, and with the help of physics and SDSU's strongest basketball players, we're going to derive a strategy for those basketball players in need. See, what these guys need is some reasoning and mathematics to allow for the perfect free throw. The first step to reaching a strategy is to understand that when the ball is released, it will follow projectile motion. When considering the ball as a projectile, it's appropriate to say that if we use its initial velocity, its path of motion will be entirely determined by the effects of gravitational acceleration and air resistance. This trajectory path follows the trail of the parabola and is detailed by a few rules and patterns to help with our calculations. First, at the top of the trajectory, the projectile has a vertical velocity of 0, but its vertical acceleration is still negative g. Second, the ball will have a constant vertical acceleration due to the Earth's gravitational pull. This means that its velocity changes by equal amounts for equal time intervals. Lastly, the ball will have a constant horizontal velocity motion. This means that its horizontal acceleration will always be 0, and it will travel equal distances per equal time interval. Knowing these rules of projectile motion, we will use SDSU's best basketball player, Paul Dalcula, to demonstrate a free throw. Paul has a height of 6 feet 2 inches and will project his arms at a 60-degree angle with an initial velocity of 5 meters per second. Let's observe. Alright guys, let's send those calculations back to Krista in the studio and see what she has to say about that.
Thank you, Ashley. That's a whole lot of physics. Good job, Paul, with that basketball. Hopefully this year, SDSU's basketball team can do a little better with the knowledge of projectile motion and the basic fundamentals of physics. Thank you, and have a nice night.
Hey Tony, this is Rainbow. Well, right here, this is the projectile motion of Paul shooting at the arc. Well, at first, we're going to find the max height of the basketball shot at the three-point line, from the three-point line. And here, Paul is about 1.9 meters tall, this is basically 6.3 feet. He's shooting at the angle of 60 degrees. His initial velocity is 7.5 meters per second. And the distance between him and the basketball hoop is about 20 feet, which is about 6.1 meters. And the height of the hoop to the floor is about 3.5 meters, which is about 10 feet. But before we find this max height, we need to derive an equation with just a normal projectile diagram. So we will go to Paul and Tyler. Thank you.
Thanks, Raymond. Now, to derive the equation, the first thing you need to do is draw a diagram. So we drew this based off of this diagram right here. It's basically the same one, except that it's broken into X and Y components, in which you have your theta, which is the same as over here, and then max height is given right here. And we start with the equation Vy equals the initial velocity of the Y component minus gravity times time. And you can say that Vy is equal to 0 right here at the max height. So it basically equals the initial velocity times the sine of theta minus gravity times time.
And to solve for this, you can use using this motion equation. You can solve for t, which is the max time it has, is the time it takes to get at max height, and we get that as initial velocity times sine of theta over gravity. And now we're going to try to solve for max height using another motion equation, which is the initial velocity of the y component times time minus 1/2 gt squared. And so we see here the velocity of the y position, like Paul said, is 0 because it's at the max height. So that's going to cancel out. This is going to cancel out. But before that, we have to plug in t. T equals, like I said before, initial velocity times sine theta over gravity into each one of these t times. So after we do that, you get that, and when you set it up, after you set it up equal to 0, you're going to get max height equals initial velocity squared times sine squared theta over 2 times gravity.
And that's how you derive the equation.
Yeah!
Gene's going to explain how to solve it.
Your name.
This is Tyler.
This is Paul. And we're Big Red.
Thanks, Paul and Tyler. Now we're going to do the solution for this problem. It's a long problem. It's taken us long amounts of time to derive this equation and draw the diagram. So basically, Paul and Tyler, they derived the max height equation, which is initial velocity squared times sine squared of theta over 2g. And so basically, this is the equation right here. And we're going to plug in our numbers. Our initial velocity is 7.5 meters per second squared. Our angle is 60, and g is 9.8 meters per second squared. So once you find this, once you calculate this, it comes out to 2.15 meters. And this is not the actual max height. You're not going to cut. You're not going to. All right. So this is not the actual max height because, as you can see, if this were the max height, we wouldn't actually make it to the hoop. What we have to do is we have to add the Paul's height, which is 1.9 meters, to this, and we get a max height of 4.05 meters, which is about where this ball is from the ground. And that is the solution to the problem. Thanks, Tony. We're Big Red.